because I forgot to record it in my other block. Okay.
Titrations can be used to determine the concentration of a specific ion in a sample solution. Here we'll see how titrations involving precipitation reactions work. Here's a setup.
Now, just before we look at the setup, what kind of titrations have we done? What kind of titration did you do when we did the lab? Who were the reactants? Acids and bases. So this uses the same procedure, but instead of reacting an acid and a base, what do you think we might be reacting? Salts and different compounds. And what would they form? A precipitate. So we're going to be looking at things that form a precipitate. And one of the things is when you get to the calculations, you will not be using the solubility equilibrium equation, the C. Okay, all the other problem types, you use the solubility equilibrium equation. But for titration, you use the precipitation equation. Did you guys catch that? Yeah. Precipitation ends the same way as titration. So you'll be writing the ions on the left and the precipitate on the right. Okay, we'll write that down later. But I just wanted to introduce that to you right now.
For a titration of a solution with an unknown concentration of Cl- or chloride ions. This long tube is called a burette. Burette can also be spelled B-U-R-E-T-T-E. This valve, called the stopcock, is closed to keep the liquid in the burette. When it's opened, liquid will drip or flow out of the bottom of the burette. In this example, the burette is filled with 0.100 molar silver nitrate solution. The solution in the burette is called the standard solution. The standard solution has a known concentration.
Okay, I'm just going to pause it there to give you a chance to write all that down. And that one. We had another name for the thing that's being called the standard solution here. Do you remember what it was? Started with a T. It was the titrant. The titrant. But the standard solution, a standard solution is a solution of known concentration. That's what standard means. And it will become a vocabulary word, not in this unit, but in the next unit. Okay, so might as well introduce it here. A lot of these concepts get used over and over again. There's going to be more acid-base titrations in the next unit, and then there will be redox titrations in our electrochem unit. So, woo, okay, super exciting, super fun.
In this case, it's 0.100 molar AgNO3. The standard solution can also be called the titrant. In this titration, a solution containing chloride ions is added to an Erlenmeyer flask and placed under the burette.
Now, just so you know, the reason it's just given as chloride ions is maybe you have taken this from some seawater or whatever, and there's chloride ions floating around, but it's not attached to any one particular ion. So you couldn't say that for sure it's sodium chloride. You couldn't say for sure it's calcium chloride. There's going to be sodium ions and calcium ions and magnesium ions floating around in the water along with the chloride. So, you guys good? Okay. What was I saying? Right? So why are we not writing any cation there? Because we don't know what the cation is. There's a whole bunch of different cations in there, and none of them are actually attached to the Cl, okay? Because it's like the ocean. It's full of all kinds of different salts. There will also be all kinds of different anions in there, okay?
The solution in the flask is called the sample. It's the solution with the unknown concentration.
Do you remember what we called that one? We had the titrant and the analyte, because we're analyzing it. Yes, analyzing it.
It can also be called the analyte, because this solution is being analyzed to find out the concentration of chloride ions in it. In this titration, a few drops of sodium chromate solution are added to the solution. The sodium chromate solution is known as an indicator in this titration. It will change color at what is called the end point of the titration. We'll show you how all of this works. We'll focus on the solutions. We'll dissociate AgNO3 into its individual ions, which are Ag plus and NO3 minus.
Okay, so there's a place for you to do that. It says 0.100 molar blank. You can write Ag plus and NO3 minus.
Science. The nitrate ion does not form any precipitates. It's a spectator ion here, so we'll just delete it from our discussion.
Okay, so that was NO3 was a spectator. Just like all of those positive ions, we don't care about them. So we're going to be working with the net ionic equation here, okay?
And tidy up a bit. So you can think of the solution in the burette as a source of Ag+, or silver ions. In a titration, we briefly open the stopcock. The solution in the burette drips into the flask, bringing Ag+ ions with it.
Isn't that a nice little animation?
Let's take a closer look at what happens in the flask as silver ions are added to it.
Now, before we zoom in and look at it, I would like you to chat with your partner and see if you can figure out what will happen when we start dripping that silver into the flask. So what happens here? Any guesses? Maybe because you're reading ahead. No, that's cheating. If you drip silver into chloride, what happens? You get a precipitate. Okay? So yeah, we're going to get a precipitate.
Now we've zoomed into the flask. Silver ions preferentially bond to chloride ions rather than chromate ions.
So when they say silver preferentially bonds to chloride, that means silver likes being with chloride more than it likes being with chromate. Okay?
This forms the precipitate silver chloride. Because silver chloride is white, the solution turns to a milky yellow color. As silver ions are added, some will temporarily bond to the chromate ions. This will form the precipitate Ag2CrO4, or silver chromate. Silver chromate is reddish-brown, so the solution will turn a slightly reddish color.
Okay, now this might happen just because the silver gets into the beaker, and even though it prefers to be with the chloride, maybe it encounters a chromate first, so it bonds with the chromate. But because it's all of those solids are in equilibrium, dissolving and recrystallizing, the silver dichromate or silver chromate will dissolve again, and then we will have an opportunity for the silver to bond with the chloride. Okay?
But silver preferentially bonds with chloride, so as the flask is shaken, the silver ions will leave the chromate ion and bond with available chloride ions, and the reddish color will go away. The solution will turn red momentarily as more silver is added, but as long as chloride is still present, shaking the flask will make the red color disappear. Added silver ions will continue to bond with the remaining chloride ions.
Now, what has just happened? There's no more chloride. So this is actually the point of the reaction we were waiting for, yes? Because we wanted to know how much chloride is there, yes? So if we know how much silver we put in, then we also know how much chloride there is because they react 1 to 1. Okay? And now the magic of the indicator comes around.
At a certain point, all of the available chloride ions have bonded with the silver ions. Since there are no chloride ions left, any silver ions that are added will have to bond to the chromate ions. The formation of silver chromate precipitate will cause the solution to turn red again. At this point, when the flask is shaken, the red color will no longer disappear. There are no chloride ions available, so the silver will have to remain bonded with the chromate.
Does this remind you of what happened when you were doing your titration? It would turn a little bit pink, and then you'd swirl it and the color would go away, and then you'd swirl it and the color would go away, and eventually the pink color stayed because you had reacted all of the acid. In this case, we've reacted all of the chloride. So we have that permanent reddish color.
We say the solution has turned a slight permanent reddish color. This is what's called the end point of the titration. A permanent color change of the indicator signals the end point of a titration.
An end point is when the indicator changes color. Okay? End sounds like end. So the end point is where the indicator changes color. Yes? There's going to be another point that also starts with an E. It's called the equivalence point, and we'll talk more about that and tell the difference between the two.
The equivalence point, or stoichiometric point, of this titration is the point where the moles of Ag+ added to the flask is equal to the moles of Cl- that were in the original solution in the flask.
So you see how we have two different points? We have the end point, which is where the indicator changes color. We have the equivalence point, so that's when these two are equal. Now, the only reason that they are 100% equal is because they react 1 to 1. If you had a 1 to 2 relationship, then one would be double the other. Yes? So just watch out for that. They are equal because they're 1 to 1, but if you had a 2 to 1, one would be twice the amount of the other.
In most titrations, if the proper indicator is used and the technique is good, the equivalence point and the end point are very close, and they can be assumed to be the same point.
Okay, so the end point and the equivalence point, if you have chosen your indicator well, and there's a whole section in Acid Base 2 where we look at choosing indicators, and you do your technique well, then you will have a good approximation, okay? So this point right here is the end point. It has turned red. Now, in order to get to the equivalence point, we need to go back here. Equivalence point. And then we add one more drop with a couple of silver ions, and we hit the end point. Okay, so it's really just like one drop. It's not enough to make a big difference, which is why we can use the end point as the equivalence point. Okay, where did we get to? There we are.
You're very close, and they can be assumed to be the same point. Once we reach the end point, we must stop adding silver ions to the beaker. This is because we want to know exactly what volume of 0.1 molar AgNO3 solution was needed to just react with all of the chloride ions that were in the sample.
Whoops, come back. There we go. So you don't want to keep going once you get to the end point. So that's when when we were doing our titration, that would be like the light pink color.
Was needed to just react with all of the chloride ions that were in the sample. We record the initial reading of the AgNO3 of 0.1 molar AgNO3 solution was needed to just react with all of the chloride ions that were in the sample.
We good? Okay.
We record the initial reading of the AgNO3 solution in the burette just before we start the titration. Then we begin the titration, adding drops very slowly while swirling the flask. As soon as the endpoint is reached, we close the stopcock, stop the titration, and record the final burette reading of the AgNO3 solution. The difference between the final burette reading and the initial burette reading will tell us the volume of AgNO3 solution required to reach the end point of the
Is this helpful in understanding what's going on during a titration? Yeah? Okay, good. I kind of like the animation. I'm like, oh, it's got all the little particles. Ooh.
this titration. And this volume will be needed for the calculations used to find the concentration of the chloride ion.
All right, and that takes us to the end of this video. There's some practice problems that you can do if you want to, but we have just done a titration, so I don't think you really probably need to. Okay, we good? So if we now go to here and here, there we are. And we're going to skip over that. Now, should you need a detailed set of instructions on how to solve a titration problem, we have them here at the bottom of page 87. If you want a review of how to do the titration calculations, this QR code will take you there. It's up to you whether you want to do that or not. I'm actually just going to summarize how to do the calculations in 3 steps rather than 5 steps. Shorten it up a little bit for you. Step number 1. Write the balanced precipitation equation. So balanced precipitation equation. And that means that the solid goes on the right. Step number 2, find moles. What's step number 3? Find moles. Titration, you find the moles that you can find. There's only going to be one substance where you have enough information to find the moles. So you're going to find those moles, and then you're going to say, oh, I got another substance. I'm going to find the moles of that substance using the balanced equation, using stoichiometry, the mole ratio. Okay, that's all there is to a stoichiometry problem. Find the moles, and you have to have a balanced equation to do that. So you have now learned all the 1, 2, 3, 4, 5 types of solubility math questions. So over the weekend, you are going to do 2 of each type, except for this one because there's more variations in this one. So I've got 3 questions there. I think it works out to 11 questions altogether. If you want to do more, you can, but you don't have to. Next week, we're going to take all of these problems and we're going to shuffle them up. Shuffle, shuffle, shuffle. So that they're not like nice in a tidy thing. If you're doing page 59, you can look back at page 58 and say, what should I do for this problem, right? If you're on page 66, you can look back on page 65, right? And say, what do I need to do? Next week, we're going to take a look at how do I recognize, what are the 5 types of problems? How do I recognize each one from the words in the question so that I can apply the right technique? Okay, so we're going to do that next week. And then we will have our quiz on that math on Thursday. Okay, and then on Tuesday, the following Tuesday, I will we'll have your test. Okay, we will be finished. We will be finished before Tuesday for sure. We'll start on acid-base 2, but I want you to have the weekend to do the review, okay, and get your quiz back, right? So I will post those test and quiz dates up on Teams. It's 13 minutes till the bell on a Friday afternoon. So if you want to work on this, that's great. If you're like, it's Friday afternoon and you just want to chill, I'm not going to get in your way. Yes. The quiz that we just did, I don't know. I have to look and see how many answers there were to question number 1. Yes. There you go.